Okay, this should be an interesting project. I have been trying to build high power switching power supplies, basically audio or RF frequency drivers, and I want to make the circuit very simple and easy to maintain. This has only got two components, but what I'd really like, see, I don't want to stick this in any permanent devices because I'm just using these slip-in, I don't know what you call it, parts as sockets, and this FET is probably not going to stay there, so I wanted to get something like a ZIF connector, and I actually ordered some ZIF connectors on Amazon, and they're taking forever to get here, but I figured maybe I'll take a look at this board, and this is actually an Atmega 328 microprocessor, like a Arduino type of thing, and so maybe I can use the board and the ZIF connector to make my high power, easy to maintain power supply. Okay, let's open this guy up. And I just come on, do some testing with this. There's some staples. Let's see if I can just pull this thing out. Back a little further. There we go. Okay. So it's got a little cardboard insert in there. And it looks like this board thing, it's actually got a 18 mega chip in there. Okay. And it looks like it is vacuum sealed. Or taped or something. Is it vacuum sealed? I don't know. Let's just cut this thing open, I guess. Get it out of there. And come on. Come on. Okay, so it looks like I mentioned some crystals and other things, but I don't really see any crystals in here. Maybe it doesn't come with it. So it comes with a couple of components here. I'm not sure what the heck those are. Maybe they're jumpers, because they have, that's not a resistors designation. And it doesn't look like it's any type of real designation anyway. And here's some headers. And let's take this foam off. Okay. And wow, okay, very interesting. Looks like the ZIF connector is not even soldered in, so I can just use this as a blank board basically. Oh, this is completely awesome. This is exactly what I wanted, a blank board. And here's our ZIF connector, and of course the ZIF connector is, you know, it's got a little lever here, so you're supposed to be able to lift up and the chip falls out. Look at that. Okay, so we got a extra 18 mega chip, which maybe I'll stick, I don't know, in this styrofoam thing, keep it safe, and stick it back in the box or something, so I don't lose it, just in case I ever have a need for another 18 mega chip. So I'll put this thing away, and I suspect these are jumpers and headers. And let me just put all this stuff in here because I'm not going to use it right now. Okay. So what I really wanted was a ZIF connector and a board to build my project on. And I'm going to copy this circuit design onto that guy. And how wonderful. Look at that. I'm going to have to check the traces, make sure that they go out, and make sure they don't short in places I don't want them to short or something. But, okay. Looks like this could be exactly what I was looking for. It's a little bit more than what I wanted to spend. Like I said, I did order some just ZIF connectors. And, let's do this. I just want to do an experiment. So here's my FET. And I'm thinking, I've been putting some thought into this. I'm thinking about having the FETs face outward, like so. Okay? So then I could have two. I could have them one in the front, one in the back, and then I can put my chip, let's see, up here. And when I put the chip, see if I can pull it out without, I'm going to try to pull the chip out of here. Maybe I need a screwdriver. It's hard. You want to be careful not to damage them. So I found that using a screwdriver will pull it out, hopefully without bending the pins. Okay. Oh, come on. Maybe I should just use a new one so I don't risk damaging this one. Okay, it looks like the pins are in pretty good shape still. I've bent them a little bit. So there's 4 pin slots up here in the front where this chip can go, and I would probably have the designation forward, the little marker thing, so that I would remember that it's pointing that way. And I'd probably put the FETs on the back side. And so you take this side, or this little lever, and you push it down. Now these things are solidly seated in there, so I could put them inside of a project without having to worry about them falling apart. And then if I need to replace it, I can flip up this little lever thing, and they easily come out, and I can put new components in if I happen to burn them out. These are the only two active components I actually have in this driver. So it is a very simple circuit, which I like simple because it's easy to fix. Cheap and easy. Maintenance is one of the most expensive things. You make something that's easy to maintain, you're going to be happy. Okay, so let me do some investigations on this board, and I'm going to trace it a little bit to see if it's going to be able to do what we want it to do. And then maybe I will replicate this power driver circuit here on this board and show you how to do that too. Okay? Should be interesting. Anyway. Okay, so here we go. I got my voltmeter, and I set it on beep so that I can measure the continuity. And so what I wanted to see is, I suspect that everything in this line is going to be connected. And yep, and then the ones next to it should not be connected. So it's just like a regular perf board. I got a nice perf board here, so I can just hook components along outside here, and it will hook to the ZIF connector, what's ever plugged into the ZIF connector here, handy dandy ZIF connector, and it really grabs those parts pretty good. So every single one of these is like a nice perf board here, radiating out from the pins of the ZIF connector. Okay, so this is exactly what I was looking for, and I'm sure it would be great for the 18 mega projects also, if you happen to want to use it for that. And it looks like it's got some other, I'm going to trace some of these other traces down to see if there's a crystal. Maybe I can use that for something else. And there's probably power coming in too. I'm going to need to hook up the capacitor, so maybe I can, if they have some traces that are convenient to use, maybe I'll jump on those. Otherwise I'll just make the circuit from scratch. I want to make sure, sometimes, you know, maybe pins are connected together or something. I want to make sure something's not shorted out that I didn't expect, because it's really a little bit difficult to see where the traces are going. So I'm going to trace this a little bit. Evil, huh? Mad science. Excellent. And it's the perfect size too. That's going to be so great. Okay, so tracing the circuit, there's a VCC up here and a ground, a VCC and a ground over here, a VCC and a ground over here, and there's 2 pins labeled VCC and ground. And if you check all these, it turns out that they're all connected together. So the VCCs are all connected together, the different points on the board, and there's a VCC pin on the circuit, which is also connected to the power, and the same with the ground. There's the ground, and there's 3 other grounds. So I'll have to decide. It's kind of not exactly where I want the power pins to be. Maybe I'll use them to route power from here to the circuit, and then use jumpers from here, or maybe there is some other ones. I'm going to trace these out. There's a crystal and a crystal clock and a ISP6. I haven't traced that out yet, and a C4. And so I'm going to see where those go, and maybe those will be useful pins as well. Okay. And a C3. I guess there's a C3 up there. Okay. So we'll see where all these wires go, and then I'll plan out my circuit from there. Okay, so just checking out some of these other connections. So these ISP are connected to the SCK, MISO, and MOSI communications. So let me see if I can do this with one hand. So I know that was one of them here. So there's traces that go. Let's see. Okay, that's that one right there. So that pin connects to that one. There's about 3 of them in here that connect to 3 of these traces in this area. Okay, so that one connects to that one. And I believe that one connects to that one. Is that right? It's one of these. Maybe there's one over here. I think one of these goes to ground. And if we look at the clock over here, the clock also has connections. This outer one goes to, well, see, there's a clock pin. There's 2 clock pins. Let's see, can I see where they are? Yeah, they're right below the ground. So there's a clock pin up there. See that? And then there's another clock pin right there, and the center one here actually goes to ground. So there's 2 clock pins that go up here, and this one goes to ground, and the ground connects to one of these capacitor grounds here too. And I think that's about it for the traces. So I'm going to maybe brainstorm on this and see if I can figure out the optimum solution to create my circuit over here on this evil genius, evil mad scientist circuit board. So maybe we can do this very simply. Okay, should be interesting. Okay, so here's our chips. Maybe I'll just stick them in the circuit to kind of get an idea of how this is going to go together. Okay, we'll lock them into place. Oh, shoot. Okay. I might just brute force this and just use the power pins as they're marked and just run wires to all the places where they need to go. And then it won't be so confusing if I'm using the proper power pins. It'll be labeled already, VCC and ground. Okay. There we go. Okay, so I think what I'm going to do is I switch the positions of these. I put the IC down at this end because then there's more room where the switch isn't to put my big ass capacitor, and I want to have this capacitor as close as possible to this switch driver because you want low inductance so you can switch things faster. Now these 2 bars in the middle, I don't know if you can see those, that they're actually power strips that run, or strips of connecting wires that run this way. And so I'm going to put the capacitor, well, let me do it this way. I'm going to do it so the, come on, the ground of the capacitor is close to the ground of the circuit board, and the VCC is close to the VCC side. And I think I'll just use this power strip to run power directly to our FET driver. and we'll make the leads as short as possible so that we can get as low inductance as possible into that FET driver. And so I think this is going to be the layout of our circuit here. I'm leaving the FET with the backside facing out so I can put a heat sink back here if I need to. Okay. So I think this is going to work out pretty nicely. Okay, so I guess I'm going to use copper enameled wire, and remember you want to strip the wire before you stick it in there. And I'm going to start with the power connectors and the positive power. Remember we had the capacitor. I removed the capacitor here, but I'm going to have the positive side on the right hand side of this bus bar that comes down, and the negative on the left hand side. And so from the positive, it comes down to the third pin from the top, or if you count these normally, it would be 1, 2, 3, 4, 5, 6. So pin number 6. And so I'm going to connect the positive to that one. And the third one down from this side is 1, 2, 3, pin number 3. Okay, and I have a wire connected to the bottom one, to the negative. Okay, and so that will be our power connectors. And I'm going to solder those on, and then I'll put the capacitor back in place over top here once we get the wires in place. Okay. Now there's different ways to strip these wires, and probably my favorite way is to use a razor blade, and you want to be careful. You can just kind of scratch the wire. Sometimes I will stick it like on the table or something, or you could use your thumb, but that's dangerous. You can cut yourself. So just scratch the enamel, and it will actually change a different color. It becomes more bright. I don't know if you can see that in the camera, but it becomes a brighter. You can see the copper better, where the enamel's not scraped off. It's more of a darker red color. Okay, and you need to scratch off the enamel at all the tips, or else you won't be able to solder to it. You won't be able to get electrical contact through it. Okay, so the next connection I'm going to make is from these bus bars to the respective, I'm going to use a VCC and ground. Since these go through the whole board and connect the power to all those, I would like to be able to connect power lines to those just in case I need them for other things. But I didn't feel like using enameled wire for those. I did have some just leads. Here's see if I can pick this up from when I clipped off resistors and made other projects. It'd be like the leads on here, where you stick them through and then you solder them and then you clip them off. And I think I'll just reuse those and just use those to make little jumpers, and I don't have to strip them. Okay. So if I just take one of these, if I can grab it off this piece of paper and bend it around in a U shape like that. Do that. Get it into a perfect U shape, and then I can just stick it in the holes that I want, like so, and there. Now we have a nice little jumper between our bus bar here and the VCC, and I'll make another one to go to the ground over here, and we'll get those ready to solder up. Okay. Okay, so there is a view of all of our wires. We got a jumper from ground to this bus bar, a wire from this bus bar to pin number 3 on our FET driver, a wire jumper from a VCC to the right bus bar over here, and then another wire up from the right bus bar to pin number 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Pin number 6, right? On the FET driver. Okay. Third pin from the top on this side. And, okay, I guess we'll keep on moving on. Okay, so if you watch my video, I did a video on damping FETs, and I think I did it on this particular power supply, and using this particular FET, and what I found is that if you want good frequency response and good switching response, you want to put some damping between some of the terminals. And I found the best terminal to damp in this particular circuit was between the gate and the drain. Of course, there's a high voltage between there, and so you got to be careful about that, not putting too much voltage on the gate. So I may have to change the design or put a capacitor in there for higher voltage stuff. But for this one, I wanted to run 30 volts. And of course, if you want to find out the power going through the FET, and hopefully it's not leaking through the gate, but it's a possibility, 30 volts times 30 volts divided by, and this is a 2,500 ohm resistor, 2,500 ohm resistor, and so that is equal to about 0.36 watts. So a quarter watt resistor will not cut it there, possibly. So you should have like a half watt or more, and I believe this is a half watt resistor. And I believe it's a gate, drain, and source. So we'll put this resistor between, oh gosh, these two leads. Let me just remove this for a second. Get this. And I was worried about not having enough wires. See, I'm going to put the resistor right there, where it's going to be between the gate and the drain. It looks like this plug is so big that it covers up some of the wires under here, but you could probably put wires under the plug and then put the plug back down before you solder it. Get extra wires onto those different pins. Okay, so there we have it. There's our damping resistor between the gate and the drain, and I'll put some more wires around that to support this transistor up here, and hopefully we'll get this device all wired up and we can start soldering it soon. Okay, so while we're wiring the simple wiring up, we'll so I have a ground connection here. It comes from the ground input up here, goes to our capacitor right here under this bus bar, and we have a ground wire that goes to our FET driver, and also the source needs to be hooked to the same ground, and so I'm going to connect a wire from this pin here, the third pin up here, to the first pin over here on the back side, the source. And so let's get a wire all set, and I'm going to scrape the enamel off and hook it between those two. Okay, so I have fashioned a wire that's about the right length with bends in it to go from those positions on our board. And you know what? I could just do it right under the board here, since or the plug. Okay. If I remove the plug, it has an overhang, so I can make that jumper from here to the source, and you want to make these as short as possible. And see, you can put the plug right over top of it, so I can efficiently use that position underneath the plug, since I haven't soldered the plug in, and I get some extra jumper spaces. Okay. Or I could do it on the outside also, but we'll see. I think I'll probably just leave it there. And there's the positions on the back. Okay, so we have our source connected to ground now. Okay. And move on. We'll be moving on. Okay, let's quickly look at our chips so we know what we're dealing with. And, oh, where did it go? Okay, so here's our FET, and like I said, it's a gate, drain, source, looking at it from the top. And of course our gate's going to be the input from our FET driver. And right now we have a resistor between gate and drain. And just out of curiosity, let's see, what's the maximum voltage between gate and source voltage? Is plus or minus 20 volts. Drain and source is 200 volts. I don't know if there's a gate drain voltage. Should be careful about that though. I'm not seeing a rating from here. Drain, source, gate, source. Okay, anyway, I may have to modify the circuit if I drive it at a higher voltage, because it may not like too high of a voltage between here and there. So I might put a lower resistance between the gate and the source at some point. But anyway, let's look at our other chip here, which is the TC, what is it? The TC 4424, I believe. Yeah, this one, TC 4424. And has no problem taking up to 18 volts. So here we have our VDD is pin 6 and ground is pin 3. And then we have actually 2 inputs and 2 outputs, so we could use either one. I think on my other power supply I used in A and out A, but we could use in B and out B as well to wire up this chip down here to the FET. And maybe I'll try that. Okay. Let me get some wires ready. So we're going to have to run a wire from the output here into the gate, and we want to make these wires as short as possible, but we also want to make this wiring easy. And if the wire is too long, it will have extra inductance and capacitance, and it will limit the operating speed of your device. I would like to make this as high performance as possible, so I could drive Tesla coils and other things as well as audio devices. Okay. So we'll see what kind of performance we can get out of this guy. And let me get some wires cut to hook. I might use the B input and output because it's a little bit closer. And I'll route something maybe around down here to the gate, which is going to be, remember our gate is the first pin on this side over here, so it would be the lowest pin, or this side of the resistor that we stuck in there already. Okay. Okay, so this is going to be the output of our, I removed our socket again so we can put some wires underneath. This is going to be the output pin of our FET driver there, which will be output B, and we're going to route the wire down to the input of the gate, which will be at this resistor down here. And so I created a J-shaped wire here to route it from, let's see if I can grab that, from up here to down here. Let's see if I can, yeah, come on, it's hard to do that with only one hand. So here's the resistor down here, and the output of our FET. So the output of our FET driver will be here. That'll be 1, 2, 3, the fourth one down, and the very bottom one will go into the input of the gate. So there's our next wire that we have, and of course that will route under our connector here. Let me just put the connector on so we can see how this is going to look. Oh, come on. Okay. So it'll look like that, and I've actually kind of routed that one wire under the connector because that connector covers up a whole row of holes that you can use. Okay. And of course the pins do go through enough so you can solder them with ease, and they go through several millimeters. So this should be fine. And that will leave those holes open in case I want to do some other stuff. You know, once you don't have a hole, then you're going to need to stick something extra there probably. And then it becomes a problem. Okay. And then I'm going to, let's see, so I got the power wired up to this guy, the ground's connected between the FET and here and the capacitor. I have the output here wired to the input of the gate, so I'm going to need to have an input voltage for the drain up here. Remember, it's gate drain, and so I'm going to clip a wire for that, and then I'm going to have an input, an external input for the FET driver, and I'll just cut those two wires now. Actually, I went ahead and made a total of 4 of them. I stripped the ends and bent the one side like so, so that okay, see, so it's just a straight wire with a bend at the end, because actually there's 2 more inputs that I need. There's a ground input and a VCC input for the FET driver, right? So I'll just get those put in there and wire those up, and I'll probably bend the wires around a little bit so they don't fall out while I'm working with the circuit, because that's annoying. Have them fall out before you solder them. And remember, we're using the B input, so that's 1, 2, 3, 4, the 4th pin down. So I'm going to put a wire coming out there for the input of that, and we're going to need possibly a different voltage for the drain. So remember, it's gate, drain, source. So the drain is on the other side of the resistor here. The resistor's right there, and I'll put our final output wire there. So I have 4 wires, a plus and a minus for the capacitor, the power supply that powers the FET driver, a signal input that goes into our FET driver, and then an extra voltage because we can run the FET at a higher voltage than where the rest of the circuit's at, so we can put more power into whatever device we want to drive with it. And so I guess that's it. I think we're ready to solder this thing up and see how it behaves. And you could, if you wanted to, take these devices out of the ZIF connector. I think I might leave them in there. A lot of times they'll have, sockets, and you can just solder the sockets on and then put your components in later. Actually, maybe I'll take them out because it protects them from being damaged by electrostatic discharge or heating it too much, even though I don't think I've ever damaged components through either of those while I've been soldering them. And maybe I'll leave them in. I think it'll be fine. And for the ZIF connector, I really only need to solder these 8 pins up here and these 3 over here, so I don't need to solder the whole thing. So let me flip this guy over. I'm going to put the camera down to do that to make sure none of my wires fall out. I'm going to bend the backs over a little bit, and I think we're ready to, let's see, that all fell out. Okay, well, maybe I'll solder them and stick them back in after I get the other components soldered. Okay, let's get soldering. Okay, so I guess what I'm going to do is I'm just going to solder these extraneous wires around here first, and I'll make sure all the wires are in place, and then I'll come back and solder the ZIF connector, because some of the wires go under the ZIF connector. And then when we're done, we'll come back and clip these leads off, and our circuit should be finished. Let me just solder this up because you don't need to watch that, and we'll check the wires, and then we'll be almost finished. Okay, so let's look at our circuit one more time under the magnifying glass. So we have the VCC here, and it comes under here to the capacitor, and it comes to the pin number 6 on the FET driver, and that's where that one ends. Then we have the ground, comes to the capacitor negative on this side, and the capacitor negative comes to the 3rd pin, the VCC negative, ground, and then it goes down to the ground of our FET down here. It's at the source, so it grounds the source to the ground of the FET driver to the negative side of the capacitor. Then we have an external input to input B, pin 4, of our FET driver, and the output is right across from it. Goes down around here into the gate, which is going to be this bottom pin down here. And then of course we have a resistor. This is a 2.5K resistor to help damp out oscillations between the gate and the drain. Okay, and like I said before, this may be a problem if you try to run too high a voltage on here, because it will start putting a high voltage on the gate, so I may have to revisit the design later for that. And of course we have a separate input for the drain, so we can put a higher voltage across the FET if we want than what we're driving it at. This circuit's only rated up to about 18 volts or so, and I'd like to put probably about 30 volts on the whole thing. So I put about 15 maybe on this one and another 15 here, we'll see, for this project. And I removed the socket here, the ZIF sockets right here, and I'm going to put that in a second after I examine all the solder joints and make sure they look good on the back. And then I'll put the ZIF socket in, solder it in, and clip the leads on the back, and we should be all set to go and test this out. Okay. Okay, so I just put the ZIF connector on here, make sure it's in the proper orientation, but I guess it doesn't make too much of a difference because I can always just put the chips in however I want. And like I said, I'm going to just solder these 8 pins up here and the 3 pins down here. 1, 2, 3 for the FET. So 8 pins for the FET driver and 3 pins for the FET. And the rest of them I really don't need the solder because I'm not using them. Okay, so let's go ahead and do that. Start soldering here. Okay. And there we go. Okay, and there we go. So there's the 8 pins up there soldered and the 3 down here. And I guess I'll start snipping off the wires and then re-examining to make sure I don't have any solder bridges or something. Maybe check out the circuit with a volt ohm meter to make sure that connections are not shorted, or connections that are supposed to be made are made properly. Okay. Might resolder a couple of these. That looks kind of like a bad solder joint. Okay. Then we'll continue on. Okay, and as I talked about in some of my videos, sometimes I use dikes to trim these. Sometimes these are nail clippers, and they can get in pretty close. Okay, I'll go trim the wires and then re-inspect them again. Okay. Okay, there they are all clipped, and it's probably not the prettiest job I've ever done, but actually I better check those two. They might be solder bridged together. But actually, you know what? It doesn't make a difference because this particular trace is running this way, so maybe that's okay. Right? Because this is a power strip down here, and this is a power strip down there. As long as it works and stays working, that's all I care about. So it looks like the solder joints are probably acceptable. I might go over them one more time. And our circuit is probably finished. I'm going to check it out a few times with the volt ohm meter, trace the circuit, make sure things aren't shorted. Because remember, you want to make sure 100% that there's no problems with the circuit before you put power on it, because that will destroy something. Of course, there's not too much to destroy here, and it's real easy to change the parts out because we have the ZIF connector here, right? You can flip it up, pull the parts out, put new parts back in, and we're good to go. So it's a quick change. It's like the Indy 500, right? Change out those parts quickly, get them back in, and continue the race. Okay. Our high performance switching power supply. Okay, it looks like I'm going to have a problem with this design because these legs in the transistor are different sized legs than these guys, and so when I clamp in the ZIF connector, these legs on the far side here don't actually make contact. See that? This chip is not making good contact because these legs here are too thick. So I may have to do a redesign here. Okay. Looks like I'm going to have to redesign this fancy ZIF thing, unfortunately. Okay, so I'm going to have to do a redesign. I think the best way to fix this is to look at the original circuit. See, I have a socket here, and that's not the problem. The socket seems to hold the chip pretty well. The problem I had is that this FET doesn't stay in there very well, and it won't be good for you know, some kind of device you don't want the parts falling out of. So the ZIF connector I think I'll just use to hold our FET transistor. Okay. And maybe I'll put a second socket down here just to hold our FET driver. Okay. And there's enough room on the board, just enough room to put this socket down here at the bottom. The socket will hold the FET driver very nicely. Let's see, get that straight. Okay, there. And so I think I'll just take off the ZIF connector and rerun the wires down to this socket for the FET driver. And that will be our new design. Okay. It might be difficult to get this FET driver off. Not sure where my wicking solder tape is. I may just have to jimmy it off slowly, which will be a pain because it's got a lot of pins. Okay, so I have my voltmeter out, and let's just test the continuity between the pins on the top of our FET and the pins down here. Make sure that it's got good conduction. Okay, I'll test all three here. Okay. Okay, so that's really all I care about, is that the transistor is making good conduction now. And so I will, excuse me, guess we'll proceed on and try to modify our circuit here. Okay. I'm going to probably take the output from here, and we're going to route it down to this new connector we're going to stick down here at the bottom. This new socket. Okay, so that'll be our new socket. And the old socket will sit back up here like so. I have to clean out the solder out of the holes, but it should all fit together. Okay. And then we can get our circuit going, hopefully. I'll probably remove this wire, the input to the FET, and move that down here, and run the power leads down to here. And then we should be all set to go. Okay, so I cut this wire back. This is the wire that goes to the gate of our FET, and I stripped it, and I think I'm going to just run it into Amplifier A. So I'll bend this thing down, and that will go into pin number, the second one from the top. It should be pin number, if we count this, 1, 2, 3, 4, 5, 6 is a power, the power pin, so pin 7. So pin 7 I have going from the gate to the output of Amplifier A on our FET driver. Okay. And then I'll probably just run a second ground down from here, and a second ground, or a second power. Actually, I accidentally cut this up here, so I'm going to run it all the way from the top all the way down to the power pin down there, and then another input, and we should be all set to go. Okay, so I just ran a new wire from the bus bar up here, connected to the capacitor on the positive side. See right there? This is the right hand side. That wire goes all the way down to where the input of the VCC is going to be, which is pin number 6, right? Pin number 6 on this socket. Okay. And so there's the power connector in there. Now I'm going to have to run a ground over to this, on this side. I'll probably run it up from, actually, maybe this pin up here, because it's less congested. Run a wire down to the pin number 3 on that side. And then I'll, of course, I'm using Amplifier A now. It's a little bit shorter, and what the heck, right? So it's going to be input on pin 2 and output on pin 7. Okay. Okay, I changed my mind. I guess that one hole that I was planning to put my wire into is full of solder, so I don't feel like dealing with that. So I'm going to run it the ground directly from the capacitor bus bar up here all the way down to pin number 3 on our socket. Okay, and I'll run it down under the ZIF connector. There should be no problem running it in between the pins. Okay, and so we got 3 over 4 wires hooked up, and I just need one more for the input of the FET amplifier, FET driver. Okay, so I just put the last wire in here into pin number 2, and so it's going to come into pin number 2, that's the input, and out of pin number 7 to the gate. Okay, so that's that circuit, and then we have the ground coming to pin number 3, and the VCC coming to pin number 6 right here. And this is not soldered in yet, so I'll probably work on getting this soldered in, and it's going to be a pain to stick the ZIF connector back in there because some of those holes are filled with solder, so I might work on that next too. And we should be all set to go. Okay, so here's our finished amplifier. I didn't put a heat sink on it yet, but I have the FET and the ZIF connector. I soldered everything up, and I put the FET driver in a separate dip chip down here. And so we have basically, what, 4 components on here. I might add a 5th one. I might add another resistor between ground and, or gate and source, and test that out so that the source doesn't get charged, or the gate doesn't get charged up too much if you run a high voltage on it. But anyway, I'll do some experimenting with that and see how that affects the bandwidth. I'm afraid about putting too much voltage on that gate. But here is our circuit, our ZIF, simple ZIF power supply. And I did a video on this SCAR speaker because I wanted to do some ultrasonics. And I also have a bunch of other speakers I'm going to be testing to see what their frequency range is in the ultrasound range. And let's just I have it hooked up to a battery, and we will just test this out to see how our circuit works. And there we go. I'm running a signal into this pin right here and connecting that to ground, so between ground and the input of the FET driver there. And of course the speaker, I did a whole video on this type of power supply. The voltage comes out of the battery, goes through the speaker, and then in through the FET and to ground, back to the battery. And you can actually put a higher voltage on it if you want, but I'm just testing this circuit out at 12 volts right now. And it looks like it's working pretty good. Okay. And so anyway, this is your simple ZIF circuit. Okay, simple high power, high speed circuit for driving either speakers, audio things, or hopefully I'll be driving some Tesla coils with it soon. Okay. Okay, so I've hooked it up to a resistor now, just using a single battery. I just wanted to test the bandwidth limit of this guy, and it looks like, so this is about 162 kilohertz, and that's still kind of a usable waveform for switching. Let me zoom in on that. I'm going to change this to 5 microseconds per division. And again, I did do a video on this digital oscilloscope. I think its bandwidth limit is about 1 megahertz. But I think we're being limited by probably the switching power supply to a little bit less than, let's bring it up to, okay, there's 200 kilohertz right there, so we could maybe still drive a coil. This square waveform is getting very unsymmetric, so it's not going to put as much power into the source or to your load. But it will definitely drive the coil at some power level. So I don't know. I built other power supplies that had more bandwidth, but they're harder to work on. If I blow a FET or something on them, they're a pain in the ass to fix, where this is going to be really simple to fix. Looks like I'll have to use Tesla coils that have resonant frequency lower than about 200 kilohertz though. Okay, let's go up a little bit higher. Okay, so there's, see, it's starting to decrease in amplitude. We're at 300 kilohertz. Okay. So I would say that's probably the 3 dB point of our power supply. It's 300 kilohertz, maybe lower because the waveform's already very unsymmetric. But let's see, we'll go a little bit higher and see what happens. That's 400. And still kind of switching at 500, but it's really, sorry, that's 460. Let's go up to 500. Okay. Yeah, the amplitude, the output's not very good at that frequency. Okay. Much better at 100 kilohertz. Okay. And anyway, very interesting. Okay, so here is our solid state Tesla coil. Let's see if I can do this. I'm going to hold this with my finger there, and I'm just going to touch the circuit here. And you can see as I'm touching the circuit, it is lighting up the neon light. So we are definitely getting power out of this thing. Let me just clip this thing on, I guess, and we'll run this coil continuously. See that? We're definitely getting high voltage out of this guy with our little circuit driver here. Okay, seems to be running pretty good. Let me unplug it and I'll see how hot the FET's getting. I don't have a heat sink on this guy. Yeah, it's getting kind of hot. It's probably going to need a heat sink. But it looks like our little evil genius ZIF connector power supply is able to drive our solid state Tesla coil. And I don't have the primary circuit matched either, so it should put out a lot more power when I match it with a capacitor of the right capacitance. I need to measure the inductance, and since we know the resonant frequency, 2.68 kilohertz, I guess we'll be able to calculate what kind of capacitance we need to drive this at resonance, and we should get a lot more power out of this guy then. Okay, should be interesting. Very interesting, huh? Definitely love Tesla coils. We'll build a time machine with this one. Okay. This is Dr. Janes, and thanks for watching.